Hi, good evening from New Zealand. Good morning to many of you. I'm very pleased to be able to give this talk in memory of our dear friend Eric, who was not only a very fine mathematician, but also a really, really good chap. And in fact, this is the last talk I have given before today. I gave it about a year ago when Eric was still here, when I visited him. And I don't apologize for giving it again. I just dedicate it to Eric's memory, because most of you anyway won't have heard it. Okay, so let's go. Let me give the background first of all. The background is mathematical economics, which I got interested in because of some strong economists in my first university 45 years ago. And they said to me that I should take an interest in this stuff because as a mathematician, I'd find lots of good problems. And it's certainly been true. And I've most of the time I've been working constructively on this. And this talk is essentially a constructive talk. So what's the problem? Well, first of all, the background. In microeconomics, classical or whatever, an individual consumer comes with a set X whose elements represent the so-called consumption bundles and a binary relation also of preference, strict preference. And so this symbolism here, where we X strictly preferred to Y, means the consumer strictly prefers the bundle of things X to the bundle of things Y. Until the 20th century, economists simply assumed that if you had a preference relation with reasonable properties, it could be described, or as we say, represented by a utility function, a mapping U from the set X, the ambient space, the consumption set, to the reals with the property that X is strictly preferred to Y, if and only if U of X is strictly greater than U of Y. If X was a topological space, I guess in the beginning of the 20th century, it would have been a metric space, maybe. If X was a topological space, then it was reasonable to expect U to be continuous. A small shift in the consumption of the bundle should result in a small shift in the amount it was or wasn't preferred to another bundle. Well, the utility representation problem grew out of that. Given a preference relation on a set X, usually with some kind of metric or other structure, prove that there exists a utility function that represents it. And if X does carry a topology, prove that there is a continuous utility function in question. Now, there are many classical existence theorems, and many of them, in fact, proved by people like de Broglie and Arrow, were Nobel Prize winners in economics. The most famous one is, in fact, due to de Broglie, and as Fred Richman and I showed in 1991, it's actually recursively false. There's a well, not straightforward, but there is a reasonably illuminating recursive counterexample for a preference relation on the unit interval. So what I want to do is to concentrate on a classical approach, which is due to Arrow and Hahn, Arrow, another Nobel Prize winner, and it's based on the rough idea that when X is a closed convex subset of Rn, and that's the traditional setting for classical microeconomics, the further the bundle B, the consumption bundle B, is from the set of elements to which A is not preferred, then the more A is preferred to B. The further B is from the things to which A is not preferred, the more A is preferred to B. Constructive versions of this theorem were developed by me in the 1980s, and I want to describe a new and, well, it's a year old now, more general constructive version of the theorem where the consumption set is actually a general metric space, not just a closed convex subset of Rn. Okay, so let me begin with what is a preference relation. So let X be a set equipped with an inequality relation, usual notation. Actually, I should have called that unequals X, as I've done down here. A preference relation, or strictly speaking, it's called a strict weak order on X, is a binary relation with these three properties. First of all, if X is strictly preferred to Y, then X had better not be equal to Y. Secondly, if X is strictly preferred to Y, then for each bundle Z, either X is preferred to Z or Z is preferred to Y. This is just negative transitivity. And of course, as you will quickly realize, if you're going to have a utility function, you're going to need these two properties. And the third one is just to get rid of triviality. There exist X and Y such that X is preferred to Y. Now, with these three properties, you can show that it's contradictory that X is preferred to X, and you can show that strict preference is in fact transitive. Now, corresponding to the strict preference, you have a thing called the preference indifference relation, a sort of curly greater than or equal. And it's defined in a positive way by saying that X is preferred or indifferent to Y, if and only if, for every Z to which Y is strictly preferred, the same X is strictly preferred to the same Z. So if you like, the least preferred Y, the least preferred object Y of the two preferred to Z means that the X is preferred to Z. And in that case, of course, X is preferred or indifferent to itself. And in fact, the preference indifference relation is transitive. We also get these simple properties. Strict preference implies preference indifference. Preference indifference implies the negation of the lower thing being preferred to the upper one. And you have this form of transitivity that strict preference basically carries through with preference indifference to leave strict preference in the end. And a utility function for or representing this strict preference is just a mapping U from X to R with these properties I mentioned before. If X is strictly preferred to Y, then U of X is bigger than U of Y and vice versa. Okay, now there's a lot of definitions in this, and I apologize that some of them are a bit technical and I haven't got any drawings to illustrate them. If I was working with a blackboard, I would, but I'll try to give a broad idea of what these geometric conditions and things are that we'll come up against. So a point A is preferred to X, a point A of X is preferred if it's greater than or equal to, preferred or indifferent to every element in X. It's non-preferred if it's distinct from, unequal to, each preferred point of X. And I'm going to denote by P sub preference relation the set of preferred points for the given relation. Now for each, these are standard definitions, for each element of the set X, the corresponding upper contour set, C of X, is the set of objects Y that are preferred or indifferent to X, and the strict upper contour set, C plus of X, is the set of Y that are strictly preferred to X. Okay, now next thing is continuity. And for that, I'm going to fix X with a metric rho to be a metric space endowed with a preference relation. And I'm looking for conditions that ensure the existence and the continuity of a utility function representing X. Classically, the continuity of U is equivalent to the preference relation being continuous in this sense, that for each element of the space, the strict upper contour set and the strict lower contour set, the set of things which are strictly unpreferred to X, the strict upper contour set and the strict lower contour set are open. That's what continuity of the utility function is in the classical theory. In which case, the sets C of X and L of X, the upper contour set and the lower contour set, are closed. And we're going to take that as our definition of continuity of the preference relation, okay? Where am I here? Yeah, well, the continuity of the preference relation will mean that the strict upper contour and strict lower contour sets are open. And we have a couple of very simple lemmas, pretty straightforward metric space things. If you have a continuous preference relation, then the set of preferred points is closed. If it's also a complete space, then the set of preferred points is complete. If the space X is complete and the preference relation is continuous, and this will come up a lot of times, the strictly preferred things, form an inhabited and located set, then the set of non-preferred points is in fact the metric complement of the set of preferred points. This is to say the set of elements of X that are bounded away from the set of preferred points. These are all pretty natural results. Now, the thing is that the continuity condition is okay, but you're not going to get the sort of continuity that you really want for a utility function from that straight condition about strict upper and strict lower contour sets. So what we'll introduce is the stronger condition of uniform continuity of the preference relation on compact sets. And this, in fact, is a kind of continuous version of the negative transitivity. It's the following. If I start with 2 points of the set X, and A is strictly preferred to B, and I have a compact subset of X, then there exists a positive R such that for any 2 points in that compact set that are R close, either the first point, either A is preferred to the first point, or this Y is preferred to, the second point is preferred to B. That's an exact sort of stretching out, continuous stretching out of negative transitivity. And if X is a locally compact space in Bishop's sense, that is, each bounded set is contained in a compact set, then UC, uniform continuity condition, implies the continuity in the upper and lower contour sets sense, and the converse holds classically, but not recursively, as a recursive counterexample to the idea that you get this uniform continuity condition out of simply the continuity condition. And secondly, if you have a continuous utility function representing the preference relation, then the preference relation does indeed satisfy this uniform continuity condition. So as it were, we're not going over the top. In the context of a locally compact space, we're not going over the top by imposing this apparently very strong condition of uniform continuity. Now, economists love this thing, local non-satiation. We say that the preference relation is non-satiated at a point A if there exists a point X which is preferred or indifferent to A. It's locally non-satiated at A. Actually, that should, it's not just preferred. If there exists a point that is strictly preferred to A, it's locally non-satiated, locally non-satiated at A if for each positive epsilon, there's a point of X which is strictly preferred to A and is within epsilon of A. And the idea of local non-satiation is fairly intuitive. It's simply saying that given any locally non-satiated point, there are points strictly preferred to it, arbitrarily close to it, so there's an incentive for the consumer to move away from a point of local non-satiation. Local non-satiation generally just means it's locally non-satiated at each point, and locally non-satiated at non-preferred points if it's locally non-satiated at each non-preferred point. Finally, locally non-satiated at a subset means that for each positive epsilon, there exists an element of the space which is within epsilon of the subset and which is strictly preferred to everything in the subset. And I use that obvious notation for meaning X is preferred to each element of the subspace. By the way, I'm not saying that in the subset, I'm not saying that the subset is located. I'm using this in the general sense, meaning that if there is a point of big S, which is within epsilon of X, then this thing holds. Now, classically, but not recursively, if you have a continuous preference relation on X that's locally non-satiated at non-preferred points and has a non-empty set of preferred points, then in fact it's locally non-satiated at each compact set that's well contained in the metric complement of the set of preferred points. So this is a fairly strong, good property, and I think we know what a metric complement, what well contained means. Just give me a second, I'm just going to shut the door. My wife is coming back from a few days away and I don't want to disturb us. Okay, now here's a key technical result, and I really don't want to go into all the details of it, but it's an essential technical result, which is quite laborious to prove. But notice something about it here. We start with a preference relation on a metric space. And what are the conditions? The first condition is that the set of preferred points is either empty or else inhabited and located. Now that condition will come up a lot, and I think I'll just refer to it most of the time as the standard condition on the set of preferred points. It's either empty or it's inhabited and located. And secondly, the second condition is that the preference relation is locally non-satiated at each compact set that's well contained in the metric complement of the preferred point set. Then I have this thing, and I'm not going to go into the details of it, it's just a technical lemma, but I want to focus or bring to your attention these two particular conditions because they will come up a lot. Okay, Well, under the hypotheses of this technical proposition, we can show that if I have a non-preferred point, then its strict upper contour set is dense in the upper contour set. And that does depend on both the conditions here, but in particular, this one here, that you're locally non-satiated at each compact set, etc., etc. So with a local non-satiation condition, you find that a non-preferred point has the strict upper contour set dense in the upper contour set. Now here's an actual theorem rather than just a proposition. If I have a locally compact space and I have my preference relation on it, and here's the standard condition on P sub preference, that it's either empty or, that should be or, else inhabited and located. And the third thing is that it's locally non-satiated at each compact set well contained in the metric complement of preferred points. Then for each non-preferred point, the upper contour set and the strict upper contour set are in fact located. And that's important because you need the locatedness of those things to construct the utility function. Okay, now this is a little tricky. This is where I would actually...
Sorry to interrupt. Can you just remind us what located means?
What, sorry?
What
located? Located means that you can compute the distance. The distance from any point to the located set exists.
Okay.
Right? Yeah, remember we're arguing constructively here.
Yeah.
Okay, now this is a tricky condition where I would really like to have had a blackboard to make a drawing, but I'll try and explain it so I hope you can visualize it. This condition is definitely new, and it's preferred point approximation. Sorry, no, this isn't the tricky one. Preferred point approximation on compact sets. And we're going to need this one as well. And what does it say? It says, if I have a compact set and a positive epsilon, then there's a corresponding delta. Well, that's a very familiar statement. And the property here is that if I start with any point in the compact set, and that point is within delta of the set of preferred points, then in fact, every point that is preferred or indifferent to the A and lies in K is within epsilon of the preferred point set. So, as it says in the paragraph here, it captures uniformly on compact sets and formally the idea that if A is in K and is near the set of preferred points, then so is the upper contour set of A as far as it's intersecting K. This condition holds trivially if the preferred point set is empty, and in particular if the preference relation is locally non-satiated. Classically, this condition holds for every continuous preference relation on any metric space. But there's a recursive example of a preference relation on 0, 1 that's represented by a continuous utility function and for which this property does not hold. So it's very definitely a property that's, while it may be classical, it's definitely non-recursive, and so you're not going to be able to establish it, to prove it within Bishop-type mathematics. Okay, and just another little useful lemma. If I have this condition satisfied on compact sets, preferred point approximation, and if I have the standard condition that the preferred point set is empty or else inhabited and located, then for any point A and any B which is preferred or indifferent to A, such that B is bounded away from the preferred points, then A is also bounded away from the set of preferred points. And if you think about that, fair enough, right? If B is preferred or indifferent to A, and its B is away from the preferred points, then surely A is as well. Now this is the tricky bit in a way, because the classical Arrow-Hahn theorem depends on the convexity of the subset of Rn that you're dealing with. So what do you do in the context of a general metric space? Well, if you analyze the proof of the constructive proof of the Arrow-Hahn theorem at Rn, you can see that you can get away with a property like this one here. And this one I've called the point-wise, well, actually you need a uniform version of it. The point-wise ball-centered distance property. Now, what does it say? Well, for each positive R and for any 2 points psi and x in the space which are greater than or equal to R, a distance apart, so psi lies on or outside the ball, the closed ball with center x and radius r, then there exists a point y, which is inside or on the closed ball with center x and radius y and radius r, and such that psi is strictly closer to y than it is to the center of the ball. Of course, in Rn, that's pretty obvious. Your ball's convex, and if you're outside or on the ball, then you can find a point which is closer to you than the center of the ball. But it didn't hold in general in a metric space. And the uniform version, of course, we need a uniform version if we're working constructively. The uniform ball center distance property on compact sets, sorry, it's such a mouthful, says that if I have a compact set K and a positive R, it's going to be a radius, then there's an alpha between 0 and 1, such that if I have 2 points of K and one of them, psi, is on or outside the ball with center, the other one, X, and radius R, then psi is not just closer to some point Y than it is to the center, but in fact, you can find a point Y in or on the ball such that the distance from psi to that point Y is less than the distance from psi to X minus alpha, where alpha is this point, this value, which depends only on K, the compact set, and R, the radius of the ball on the compact set. So it's a uniform version of the previous thing that we had. Now, of course, the pointwise version implies the uniform one implies the pointwise one. And if you look at a straightforward contradiction, sequential compactness argument shows classically that these two are in fact equivalent conditions. And significantly, what we have is this, that every inhabited convex locally compact subset X of a Euclidean space has the uniform ball center distance property on compact sets. So this is definitely a generalization from the Rn situation to the general metric space. Okay, right, so what's the theorem in question? I'm not going to hint how to prove it. It's a long and complicated proof. So let's get the data right. We start with our locally compact metric space, and it has the uniform ball center distance property on compact sets. That's our substitute for convexity. And it has the property that each open ball is dense in the corresponding closed ball, which of course holds in Rn. I have a preference relation that's uniformly continuous on compact sets. Remember that that's a kind of uniform or stretched version of negative transitivity for strict preference. The preference relation also has the preferred point approximation on compact sets, and it's locally enunciated at each compact set that is well contained in the metric complement of the preferred point set. Of course, it can't be locally enunciated at a preferred point. So these are all fairly reasonable conditions on the preference relation and the space. Suppose also our standard thing that the preferred point set is either empty or else it's inhabited and located. Then we can actually construct the utility function we're after as follows. First of all, we observe that from the earlier stuff, for each point of the space, the upper contour set is locally compact. That's number one. It's complete, and it's located, and it's locally compact. Now, if x0 is a point in x that we're going to keep fixed, and Rn is an increasing sequence of positive numbers diverging to infinity, such that for each n, the closed ball Bn, namely the closed ball with center x0 and radius Rn, is compact. So this is just picking out a particular sequence, increasing sequence of closed balls centered on x0 that's going to span the whole locally compact space. In that case, for each x, I can show that this thing called un of x, a temporary utility function, which is the supremum of the distance from psi to the upper contour set of x, where psi belongs to the nth ball. That exists for each n. And if I combine those UNs by taking the sum with the multiplier 2 to the minus n for the term and UN over 1 plus UN, that ensures, first of all, that each of these terms is less than 2 to the minus n. So the series is convergent. And in fact, it defines a continuous utility function representing the preference relation. So this is actually, this construction is similar to the construction of the utility functions is similar to the one for the Rn case. And it's actually an improvement on the classical Arrow-Hahn one, because they go into all sorts of convoluted things to construct, in their terms, the utility function. But this is much more explicit and actually a more simple construction in that sense. Okay, so let's recall that with classical logic, we can prove the following for a preference relation on the metric space X. First of all, that if X is locally compact and the preference relation is continuous, then it satisfies the uniform continuity and compact sets, etc. The pointwise ball center condition implies the uniform one, classically. If the preference is locally non-satiated at non-preferred points, then it's locally non-satiated at each compact set well contained in the metric complement of the preferred point set. And if it's a continuous one, then it satisfies the preferred point approximation condition. So in fact, a whole bunch of our constructive conditions are satisfied classically automatically by a preference relation with continuity, pointwise ball center condition, this local non-satiation away from non-preferred points, at non-preferred points, and the continuity implies the uniform preferred point condition approximation. Notice also classically a metric space is locally compact in the constructive sense if and only if it's a classically locally compact space, that is every point is a compact neighborhood, and is separable. So we're essentially, from a classical point of view, we're looking at preference relations with pointwise conditions on a separable locally compact space. Then we get a classical extended Arrow-Hahn representation as follows, simply with all these pointwise conditions, namely separable locally compact space with the pointwise ball center distance property. Each open ball is dense in the closed ball. We have a continuous preference relation that's locally non-satiated at non-preferred points. And then we define the same thing we did in the constructive construction, and we get a continuous utility function representing the preference relation. So this is a classical generalization of the Arrow-Hahn representation theorem. Okay, one or two concluding remarks. There are classical utility representation theorems when X is a non-metric topological space, but lifting the Arrow-Hahn distance function approach, which is a very geometrically intuitive one, to the preferences on abstract metric spaces rather than finite dimensional Euclidean spaces is something which seems to be completely new. And the ball center distance property, again, seems to be new. I've never seen anything like that before. And in either its pointwise or uniform version, it's something that's probably worth investigating as a generalization of convexity. It might be useful in optimization and approximation theory. And finally, actually, this is not quite correct because this thing has appeared. The actual paper with all the details in it has appeared in a Springer volume in honor of my co-worker Ghanshyam Mehta's 75th birthday in a volume called Mathematical Topics and Representations of Ordered Structures and Utility Theory. Economists seem to like really long-winded titles for their books, but you can actually get that, but of course you have to pay for it. Okay, and I think that's me. Yes, that is me. Sorry, it was a bit rushed, but I didn't want to waste too much of your time.
Okay, thank you very much, Douglas. It's very nice. Should we do a silent applause?
I don't think we should.
All right, great. Let's open the floor for questions. So any questions, just unmute your mic or post it in the chat.
Everybody's dumbfounded. Oh,
can I ask a question? I mean, this is a bit basic, but
oh, I see. Yep.
The mathematics is quite all very precise. Is how much of that precision is justified by the accuracy of the, the kind of Homo economicus model of preferences?
Oh,
Do people really behave like that?
You should ask that to any theoretical economist, classical or otherwise. I'm honestly not making any claims that this is of massive economic use. It's really a problem in representation of ordered structures, essentially. It's a kind of topological algebraic problem of which there is a lot of classical stuff done. The fact that it's motivated by economics doesn't mean that it necessarily feeds back into economics.
Okay, so to turn the question around, are there any mathematical applications of what's going on here?
Not that I know of, but if you look at the classical literature, that you will find them. I mean, it's a big area of often just published under economics, but it is a big area of actually not only economics, but mathematical psychology and so on, this representation of various types of preference ordering by utility or other functions. It is considered quite a significant subject.
Thanks.
Thank you. Any other questions? So I'm kind of curious. So how much? So what do the economists think of all this? Do they just view it as some kind of mathematical curiosity, or are they?
Well, it depends. I mean, the theoretical economists would be interested in this kind of thing. Of course, persuading them that the constructive approach is interesting is maybe a different matter. But just trying to think what they. I mean, there are books about the whole general business of this kind of stuff. In fact, one of them was written by Gancha, Mehta, and me. It's a Springer lecture note, and it's actually totally classical. There's no constructive things in it at all. I sinned. I went classical to write this.
Okay.
How do the economists react to it being constructive? Do they care at all about the difference between constructive or non-constructive?
I very much doubt it, but I'd like to. One might ask how many mathematicians care these days. Unfortunately, it's better than it used to be, but it's certainly not perfect. I very much doubt it, actually. Yeah.
Okay. Any other questions for Douglas? All right. Okay, let's thank Douglas again with another silent applause over Zoom.